All right, so we're talking about the stereoisomers of alkanes. What we're talking about are chiral molecules or molecules that have chirality in them. And so what this means is that it has a non-superimposable mirror image. And the best example here is your hands. Right, you have kind of a left hand. Oops. Right, there's my drawing of a hand. And then this is your knuckles right here, I guess. And then if you think about what a mirror image would look like, it would look just like your right hand. But you cannot superimpose one on the other, right? You can't place one hand over the other and have them perfectly match. Your thumbs are going to get messed up, or your palms aren't going to face the same way, right? And so we can say that our hands are chiral because they have mirror images of one another that are non-superimposable. And so why does this matter? Right? Who cares? And then the question is here is, can you put your left hand in a right-handed glove? And the answer to that question is obviously no, right? If the glove is fitted for one hand, the other hand won't really fit in there. Well, molecules are the same way. So let's draw a carbon. And we're just going to draw in this little tetrahedral form, and then it's going to have 4 bonds to things. Up top, we'll put this kind of yellow circle, over here, orange circle, here, purple, and then here, green, right? And so one of the big things we study for organic chemistry is to see how it interacts with life, right? And so in your body, you have all kinds of receptors for tastes, for feel, all kinds of different stuff. And these receptors fit molecules inside of them, but they're very specific in which way they fit the molecules. So for example, maybe this receptor has an orange spot here, a purple spot here, and a green spot here. And so you can see here that your molecule will perfectly match to these receptors. And so when this molecule gets into this receptor, right, it's going to fit, and then it's going to send some kind of signal. Maybe this is like a taste receptor, or maybe it's, something else, some kind of hormone or whatever you want it to be, right? And so we can think about the mirror image of this molecule then. So if we draw the image, the wedges and the dashes are going to be facing this way, and this part will be facing away. So orange or yellow up top. This time orange is going to be far from the mirror. Purple is going to be closer to the mirror and sticking out, and then green will be closer to the mirror and sticking to the back. And then we'll draw this same receptor, right? So the receptor goes orange, purple, and then green. And so you can see here, if this molecule over here tries to go into this receptor, there's going to be a mismatch, in this case between this green and this orange sites. And you can try to rotate this, right, about this bond, but no matter what you do, it's not going to fit in there. So let's go ahead, rotate them. Let's move the orange one back here, green one here, and then purple one here, and then yellow on top. And then you can see it's still not going to fit, right? This green and this purple are going to mess things up. And you can keep rotating it. No matter what you're going to do, it's not going to fit. And so if this doesn't fit in the receptor, there's going to be no signal sent or no modulation downstream. And so you can see how whether your molecule is left-handed or right-handed can affect what kind of properties it has.